Friends, welcome to the 36th lecture on Advanced Steel Design, where we are going to learn something about unsymmetric bending. So, we call this unsymmetric bending lecture 1. In the previous lectures, we have learnt the importance of plastic design, form resistant design, material properties at elevated temperature for steel, newly proposed materials as functionally graded materials and their advantages. We have also did some examples on plastic design and analysis. Then for form dominant design, we understood that stability, which is one of the modes of failure, is important to assess, and we developed stability functions for various application conditions of axial compressive load, axial tensile load, and etc. And we did some problems and used MATLAB intensively to find out the critical buckling load so that I can assess stability of these systems. Now, unsymmetric bending is another area of challenge in advanced design procedures. Generally, friends, in symmetric bending, bending takes place in a plane parallel to the plane of applied moment. Let us try to explain this with some graphical illustration. Okay. So, let us take a beam. So, let us say this is my x axis of the beam, which is along the span of the beam. Let us call this as y, and you know the z axis is normal to this laptop screen. So, with that axis, I apply a moment about that axis. I call that as mz. So, mz is the moment about z axis whose trace is seen on the xy plane, right. So, now if I cut a section, okay, if I cut a section, and if the section, cross section is known to me, where this becomes my x axis now, and I will call this as y and this is z axis, correct. Imagine this figure 1 and figure 2. Figure 1, positive z is normal to the laptop screen, okay. Look it from the side. So, you will see y in the vertical direction and z towards left side, am I right? So, I think I will remove this, write it better here, and remove this, maybe write it here, okay. So, now I can say a word in the cross section of the beam, y axis is the trace of applied moment. ZZ axis is the axis about which moment is applied. Okay, we call that y as mz. Okay. Having said this, we can now write a condition saying bending takes place in a plane parallel to the plane of applied moment. So, therefore, friends, we know that moment about y axis is kept as 0. Mathematically, algebraic sum of moments about y is 0. We call C equation number 1. Therefore, there are no external moments acting about y axis. Right. Since there are no external moments acting about y axis, the internal resisting moment about y axis should be 0. So, can I say mathematically my should be integral of over area A sigma x dA, okay, with 0 equation 2. Okay. So, now we also know stress by y is E by R, hence E by R into sigma x dA of the area A should be equal to 0. So, now sigma x is the product of moment of inertia. So, let us do that way, saying it should be same as over the area A, I should say zy dA should be termed to 0. We call this as equation 3. Okay, do not mistake it as stress, it is not stress. Okay. To ensure this condition, we should imply that this should be satisfied. So, we can say zy dA should be termed as 0, we call this as 3a. The above equation is only true when zz and y axis are principal axis. Okay. The above equation 3a is true only when zz and y axis are principal axis. Hence, for the symmetric bending, there are certain conditions. 1, it is essential that the plane containing A, principal axis of inertia, B, plane of applied moment, C, plane of deflection. Should coincide. Then only a symmetric bending can happen. The second condition for symmetric bending to happen is it is also obvious that the neutral axis will coincide with other principal axis of inertia. So, therefore, friends, when the trace of plane of applied moment does not coincide with any of the principal axis of inertia, then it is called unsymmetric bending. This is also called by another name, which is non-uniplanar bending. This is another name of unsymmetric bending. Okay. Now, the question comes, if a member or a cross section is subjected to unsymmetric bending, what will be the consequence? So, we will ask a question, what are the consequences if a member is subjected to unsymmetric bending? Okay. First, the neutral axis will not be perpendicular to the trace of the applied moment plane. It makes an inclination. Okay. 2, the deflection curve is also not a plane curve. Or we should say will not be a simple plane curve in the plane of applied moment. Three, members which are not symmetric, because you may get members which are not symmetric in cross section. So, members which are not symmetric about the vertical axis and have a special cross section, then these members will undergo twisting under transverse loads. Okay, that is a very serious consequence we have when the members are subjected to unsymmetric bending. The fourth could be to avoid twisting of unsymmetric section, load should be applied at the shear center. Now the question comes, what is the speciality in analysis if a member is subjected to unsymmetric bending? The answer is the applied moment in such cases will cause bending about both the principal axis of inertia okay. Therefore, stress at any section or at any point in the cross section cannot be determined using the classical theory of bending, that is E by R is stress by Y is M by I. This equation cannot be used to determine the stress. Okay. So, it is very complicated problem now. Now, what do I do to determine the stress when a member is subjected to unsymmetric bending? So, the question is then how to determine the stress? At any point in the cross section of a member under unsymmetric bending. Okay. To do that, it is necessary to transform the problem of unsymmetric bending into uniplanar bending. So, we need to do a transformation of the problem. Now, the question comes, how will you transform the problem into an uniplanar bending? Okay, that is an interesting question because we need to find the stresses at the cross sections. Let us look into that. So, the objective is now to transform unsymmetric bending. Problem 2, uniplanar bending. That is objective now. Okay, let us take a cross section. Okay. Let us mark these two axes as Z and Y. Okay, X is normal to the screen. Okay. Let us also mark two more additional axes which is called the V and U axis. Let us measure the angle of U axis from Z axis or V axis from Y axis as alpha. Okay. Let us take a point whose area is dA. It has got specific coordinates u and v or x y depending upon our choice of coordinates. Okay. Let us refer this as figure 1, a typical cross section of a member. Okay. One can very well see here that UU axis is inclined alpha to ZZ axis. Alpha is measured from ZZ axis clockwise to mark UU axis. Okay. That is a condition here. So, to be very specific, alpha is measured in the positive V coordinate. So, we have positive V, we measure from that. Okay. So, from this figure I can write a basic relationship which is very easy. Write down that. So, from figure 1 we can write the following equation. What are they? U is given by Z cos alpha plus y sin alpha. V is given by minus Z sin alpha plus y cos alpha. We call this equation number 1. It is a basic equation written with reference to figure number 1. Is it not? Okay. Having said this, I want to find the moment of inertia. Let us say to find the moment of inertia about UU and VV axis. Remember, they are inclined to ZZ and YY. So, it is not that easy to use a principal axis, parallel axis or perpendicular axis theorem to find out that. Okay. They are inclined by an angle alpha. So, it is not that easy to find out IUU and IVV. So, let us use first principles. So, from first principles, we know IU is integral V square dA for the whole area A. IV is integral u square dA for the whole area A. We call this equation as 2E. Okay. Now, we have expression for u and v. Do we have expressions for u and v? Let us substitute it here and see what happens. So, now IV becomes integral over area A, u is z cos alpha, okay, v is minus z sin alpha. So, minus z sin alpha plus y cos alpha the whole square dA. So, I am getting I am getting IU, okay, IU. I am getting IU. So, V is here, I am using this relationship, okay. Let us expand this. So, let us say IU is equal to integral z square sin square alpha plus y square cos square alpha minus 2 zy sin alpha cos alpha of dA. Okay. So, which will be sin square alpha of z square dA whole area A plus cos square alpha of y square dA whole area A minus sin 2 alpha integral zy A dA. How do we write this? We know sin 2 alpha is 2 sin alpha cos alpha. We know this, is it not? We also know from the first principles that z square dA for the whole area A can be said as Iy integral y square dA for the whole area A can be said as Iz. Okay. When we know this, then I can write Iu from the our equation as Iy sin square alpha plus Iz cos square alpha minus I yz sin 2 alpha. Okay. We will call this equation number 2. Let us simplify this. Let us copy this equation here. I will use a tool. I will copy this equation. Okay. Let me copy it here. Okay. So, I am going to simplify this equation. Let me remove this number. This is equation 2. We know cos 2 alpha is 1 minus 2 sin square alpha, which is also equal to 2 cos square alpha minus 1. So, therefore, sin square alpha is 1 minus cos 2 alpha by 2 and cos square alpha is 1 plus cos 2 alpha by 2. So, I am going to replace these two values with these new expressions. Therefore, I can now get IU as IY by 2 1 minus cos 2 alpha plus IZ by 2 1 plus cos 2 alpha minus IYZ sin 2 alpha. Am I right? We can further simplify this because I have IY by 2 and IX by 2. So, I can say now IU is IY by 2 plus IZ by 2, this is 2, okay, 2 plus IZ minus IY by 2 cos 2 alpha minus IYZ sin 2 alpha. So, can I now say IU as IY plus IZ by 2 plus IZ minus IY by 2 cos 2 alpha minus IYZ sin 2 alpha, called equation number 3. So, let us take equation number 3 as one of the important reference derivative. Now, let us move on to IV. Now, let us find IV. We know IV is integral u square dA for the entire A. We already know u. We already know u. As this value, is it not? Z cos alpha plus y sin alpha. Let us substitute it here, which is going to be equal to integral for the whole area Z cos alpha plus y sin alpha the whole square dA. Let us expand this, which will be Z square cos square alpha y square sin square alpha plus 2 zy sin alpha cos alpha of dA integrated whole area. Now, I can write IV as cos square alpha integral Z square dA for the whole area A plus sin square alpha integral y square dA for the whole area plus sin 2 alpha integral whole area zy dA. I think there is no confusion in writing this expression. Now, I can write this as Z square dA is IY cos square alpha, y square dA is IZ sin square alpha plus this is going to be IZY sin 2 alpha. This is IV, is it not? Now, let us take this IV and expand it. As we have the substitution. So, now IV is expanded as one plus cos 2 alpha into IY by 2 plus 1 minus cos 2 alpha into IZ by 2 plus IZY sin 2 alpha. Now, IV can become IY plus IZ by 2 minus Iz minus Iy by 2 of cos 2 alpha plus Izy of sin 2 alpha. Okay, we call the equation number, maybe 3 is here, we call this as 4. So, for our simplicity, let us copy this equation 3. I am using a selection tool and copying this equation. And putting it here. Okay, this is the equation, I am writing it here, right. I will rub this, put it here. So, Iu is Iy plus Iz by 2, Iz minus Iy by 2 cos 2 alpha minus Iuz sin 2 alpha, whereas Iv is Iy plus Iz by 2 minus z minus y by 2 cos plus z by sin. So, if I add equations 3 and 4, what do I get? So, if I do that, z minus y plus this goes away, this goes away. So, I can straight away say Iu plus Iv is Iy plus Iz. Am I right? I get this classical relationship. I call this equation number 5. Okay, it is a classical relationship. Let us also find out the cross product, which is Iuv. We know Iuv is given by integral uv dA over the area A. So, we already have the values for u and v. We see here in equation, we have equation 1, we have u and v. So, let me write it here. So, substitute for u and v from equation 1. So, let us do that, which will be equal to integral z cos alpha plus y sin alpha into minus z sin alpha plus y cos alpha of dA for the whole area, which will now become integral minus z square sin alpha cos alpha, okay, minus yz sin square alpha plus yz cos square alpha plus y square sin alpha cos alpha. Am I right? This is for the whole area. Okay. Let me copy this equation . Take it to the next screen for our reference. Okay, which is now, this is Iuv, is it not? So, Iuv is now, so we have two terms, sin alpha cos alpha twice. Okay. So, what I will do that is, I can write sin alpha cos alpha integral z square dA, let us have a minus sign, plus sin alpha cos alpha integral y square dA plus okay, yz dA, okay, we will do it this way, plus yz cos square alpha minus yz sin square alpha dA for the whole area. Am I right? Okay. So, now I can expand this further. So, we know this is minus of Iy sin alpha cos alpha, and this is Iz. So, plus Iz of sin alpha cos alpha plus, you know, Yz dA is Iyz, is it not, of cos square alpha minus sin square alpha. Am I right? Which now amounts to Iz minus Iy of sin 2 alpha by 2 plus Iyz cos 2 alpha. Equation 6. This is my IUV. It's a classical equation. Okay. Friends, we must subsequently substitute IUV to be 0. So, not subsequently, we should substitute IUV as 0. Why do we have to do that? In simple terms, IUV need to be indicated as an understanding of explaining the unsymmetric bending. So, now friends, U and V being principal acts of inertia, IUV should be 0. Okay. So, what is IUV? I am just copying this equation. So, if we equate this to 0, okay, I will get tan 12 is minus twice Iyz by z minus y. Am I right? Is it okay? We call this equation number 7. Okay. So, friends, we are now interested to find out stress at any point in a given cross section. Okay. So, our objective is to find stress at any point in the cross section. That is the objective, is it not? So, we will look into this in detail in the next lecture. Let us now write the summary what we learned in this lecture. We learned what is meant by unsymmetric bending or non-uniplanar bending. We have also learned what are the consequences if a member is subjected to unsymmetric bending, if I want to find the stress at any point P in a cross section or a member under unsymmetric bending, what do I do? What do we or how do we calculate? So, we said that we need to convert the unsymmetric bending problem into an uniplanar bending problem. To do that, we need to find the principal moments of inertia, and we equated the product to 0 being principal axis and to find the inclination of alpha. Remember, alpha is an angle, okay, is an angle of UU axis with ZZ axis measuring from the positive Z to positive U or positive V to positive Y, okay, in a specific manner. So, if I know this, using the equation we will be able to find the stresses, okay. That is what we discussed briefly, and we will explain the equation how to find stresses in case of an unsymmetric bending in the next lecture. Thank you very much and have a good day.